Okay, this is a quick presentation on temperature measurement in about 10 minutes, and just quickly look at the different issues of temperature measurement. Brief discussion of thermocouples, RTDs, thermistors, and a brief mention about parameters and some of the issues with installation. Two main types of temperature measurement: contact, where you have thermocouples, RTDs, and thermistors, and obviously non-contact as well, with particularly infrared. Thermocouples are probably the most common. Two dissimilar metals, iron and constantan, electrically connected. You have heat applied to the junction. You have a voltage across the two wires as a result of the heat, and very low voltages, microvolts. So here's a typical example of a thermocouple. Measurement done there at the tip. You need cold junction compensation to relate it to a common reference point. Basically, the idea is that the thermocouple generates a voltage based on the Seebeck effect, which is basically a voltage potential across two dissimilar metals. There's also two types of cables, extension and compensating cables used. There's various strategies here with averaging temperatures, swamping resistors, thermocouples to measure the temperature difference, different strategies here. The construction of a thermocouple is basically fusion welded to form a pure joint. It's very important that you have a high integrity joint, otherwise you have all sorts of problems later. Not immediately, but later when you're running the system. Grounded junctions, which I'll come back to in a tick, are very useful for good thermal contact, but you do have potential problems with earth loops. So ungrounding junctions are quite useful for electrical isolation, but you have a little bit of a process delay as a result. There's insulated junction, bonded junction, in other words, very low process delays, and exposed junction as well. Insulation techniques are to use the largest size thermocouple while possible, avoid stress and vibration, and use transmitters as possible to try and boost the voltage or the signal. The suggestion here, measure the resistance continuously to note any changes, and shorts and extension wires is not always easily detectable. Thermopaste is useful to eliminate any problems with air gaps in the thermal well. Grounding requires care, and extension cable may also need to be replaced. Here's a few typical curves with thermocouples. As you can see, millivolts, and obviously the temperature range along the x-axis. And discussion about different applications. You have different thermocouples with different ranges of temperature. Advantages are stable, wide range of operation, fast response, robust, small, and obviously cheap. Disadvantages are it's a very low voltage output. It's non-linear, so you've got to linearize it. Limited accuracy, sensitive to electrical noise. And there's a bit of a complex conversion from the EMF to the temperature. It's quite a complex conversion. Let's see other little examples. Yeah, the other device is an RTD, which is quite useful. Platinum, probably the most famous one is PT100 or indeed PT1000. And the idea here is simply you've got four ways of measurement. Essentially, your platinum, as it's heated up, your measurement, will cause resistance changes. So in other words, as your temperature goes up, the resistance goes up as well. 2, 3, or 4 wire. Basically, 4 wires are the best in terms of 2 wires are used to provide you with a constant current signal, and 2 wires are used to measure the changes of the voltage. A few strategies there. The PT100 is housed in a thermal well. You could use 2-wire for HVAC where you're not too concerned about accuracy. Industrial applications, 3-wire, and high precision, use a good old 4-wire. One of the challenges with RTDs is obviously self-heating of the junction because you're providing with a constant current source. Advantages are good sensitivity. You standard copper wire to connect. You don't have the thermocouple effect, and generally you have a fairly linear response curve. Disadvantages are it can be a little bit fragile. You can get a self-heating issues, susceptible to noise, and sometimes expensive to test and diagnose any problems. Fairly bulky as well. The other famous device is the thermistor, where you get temperature changes. As the temperature goes up, the resistance goes down. So you get a negative temperature coefficient. So here's a sort of typical curve. Thermistor's resistance goes, as the temperature goes up, your resistance drops. Typical examples of thermistors. Advantages: small size, fast response, high sensitivity, inexpensive, no cold junction, polarity insensitive. You can get a wide selection of sensors. Disadvantages are nonlinear, which you can see in that previous graph. You get that curve looking like this, which is very decidedly nonlinear. Fragile, high resistance, noise problems, not easily interchangeable, and you get some drift and decalibration over time. So the other device is liquid and glass filled by metallic. Not going to worry too much about that. Bimetallic, here we are. Non-contact pyrometers are the other major device. Infrared and acoustic. Those are the other two major devices. Humidity sensors. Some of the installation issues, which I mentioned earlier on, is that you could get a thermocouple which has a very low process lag because it's actually connected to the sheath here. So your temperature changes are transmitted rapidly through. Any problem is you get an earth loop forming, and that can cause a major problem. So watch out for that particular issue. Here's a typical example of different outputs versus temperature for thermistors, RTDs, and thermocouples. And that's about it from Steve Mackay at Engineering Institute of Technology. Thank you very much.